Let us recapitulate our study on orthogonal expansion of signals. What we studied was, given a set of orthonormal basis signals and any signal ST, it is possible to approximate this signal ST in terms of the weighted linear combinations of this orthogonal basis signals in such a way that the energy in the error signal is minimized. And we saw that this is achieved by taking the first derivative of the energy with respect to the coefficients of expansions and equating this to the zeros and solving the equation, and the result we got was that the error signal turns out to be orthogonal to all the basis signals which we use in the linear combination to approximate the given signal ST. Now suppose that we have a set of finite energy signal waveforms SMT, where m goes from 1 to capital M, and from this set we wish to construct a set of orthonormal waveforms. So to achieve this, we follow what is known as Gram-Schmidt Orthogonalization procedure. This will allow us to achieve our objective The procedure is very similar to the one which is used for vectors. Okay. So, let us look into this procedure. The first basis signal can be chosen as follows. It is the S1T and you normalize with the energy of this S1T, correct. Your S1T energy is given by this integral. Without loss of generality, we are assuming that all our signals are real signals. Okay. So, what this specifies that if I choose my basis signal phi 1 t to be equal to S1T divided by the root of E1, then I am able to express my S1T as root E1 phi 1 t. Okay, fine. Now, let us use the signal S2T in the set. We define the coefficient S21 as projection of S2T on phi 1T. So, what we are saying is that we are trying to find the linear combination of S2T in terms of phi 1T such that energy in the error is minimized, correct. So, then I will get a new intermediate signal which we define as G2T. This is basically nothing but the error signal between S2T and its approximation using phi 1T, correct. Now we know from our study on orthogonal expansion of signals that this error signal is going to be orthogonal to phi 1T over the interval we are using this interval without loss of generality. Okay? So, if we do this, therefore, we define the second basis signal as that is this error signal, and we normalize by its energy and this can be rewritten as follows. We have seen this earlier that this quantity would be equal to E2 minus S21 squared. Okay? What we could do is basically take S3 this signal and try to express it as a linear combination of phi 1t and phi 2t, correct, and then get the error signal of approximation between S3t and this linear combination of phi 1t and phi 2t. So, we will get an intermediate signal that is G3t. Now, G3t will be obviously orthogonal to phi 1t and phi 2t, correct. So, that could be used as another basis signal after normalizing it with the energy of G3 signal, square root of that. Okay, fine. So, in general, I can always form a new intermediate signal as follows. GIT is equal to SIT minus linear combination of basis functions which have been computed earlier. So, there will be I minus 1 basis functions and your coefficients of expansion, that is Sij, would be equal to projection of Sit on the basis function phi j t, correct. And then we can get my basis signal phi I t to be equal to G I t normalized by the square root of its energy, which can be rewritten as this is EI, the energy in a SIT signal, minus fine. So, the orthogonalization process is continued until all the m signal waveforms have been exhausted and n less than or equal to m orthonormal waveforms have been constructed. So, the dimensionality n of the signal space will be equal to m if all the signal waveforms are linearly independent. What it means that none of the signal waveform is a linear combination of other signal waveforms. Okay. So, let us take an example to appreciate what we have done. So, let us say that I have 4 waveforms given as shown here, S1t, S2t, S3t, S4t. Okay. So, what we will do is basically we will start with this and let us try to obtain the orthonormal basis signal in terms of which we can represent any of this given 4 signals. Okay. So, we will choose from this. The solution would be as follows. So, S1t, its energy is equal to 2 square root multiply by t, so 2, correct. So, my phi 1t is equal to 1 by root 2 S1 t. Next we observe that S21, that is the projection of signal S2t on S1t, is equal to 0. Hence, this implies that S2t and phi 1t are orthogonal. This means orthogonal, correct. Therefore, I can choose my phi 2t to be equal to S2t normalized by the square root of its energy. And again, in this case, if you see, the energy in the signal S2t is equal to 2. So, root of 1 by 2 S2t. Okay? Fine. So, now we proceed to obtain phi t. So, for this we need to compute the projection of S3t on phi 1 and phi 2. So, these are the coefficients which are S31 is equal to root 2 and S32 is equal to 0. Very straightforward from here, correct. Looking at this itself figure, we can see that the projection of this onto the phi 1t is similar to this, correct, except for the normalizing factor of root 2, correct. So, you will have the projection of this on phi 1t, but the projection of this on the phi 2 which is similar to this except for the normalization will be equal to 0. Okay, fine. So, this we will get. Therefore, my G3t will be equal to S3t minus root 2 phi 1 t, and this would be equal to minus 1 for this interval and it is 0 otherwise. Correct? So, since GT3 S3T has unit energy, it follows that your phi 3T is equal to G3T, correct. Now, we have to still proceed. So, determine phi 4T, we find S41 is equal to minus root 2, correct. So, projection of this on phi 1T will be equal to minus root 2, S42 would be equal to 0, correct, fine. I am showing this because phi 2T is similar to this, okay, and S43 would be equal to 1, okay. So, hence my G4T would be equal to S4T and this turns out to be 0. So, what it means that S4T is a linear combination of phi 1T and phi T3, and hence phi 4T is equal to 0, okay, fine. So, based on this, the 3 orthonormal basis signals which we have computed are shown here, phi 1, phi 2, phi 3. So, this resembles S1T except for the normalizing factor, this also resembles S2T except for the normalizing factor, and this is really different from S3T, correct. So, once we have constructed the set of orthonormal waveforms, in this case we have got 3 orthonormal waveform, we can express the 4 signals which were given as linear combinations of this orthonormal waveform, correct. So, in general, once I have my orthonormal basis signal, I can express my signal SMT as linear combination of basis signal, correct. So, in our case this M would go from 1 to 4, this capital N would go from 1 to 3, sorry, this capital N would be 3, correct, this N would go from 1 to 3. So, based on the above expression, each signal may be represented by the vector. So, I can represent it as a vector like this. In general, this will be n, or equivalently as a point in the n dimensional signal space, correct, with coordinates therefore, what we have shown that a set of m signals can be represented by a set of m vectors in the n dimensional space where n is less than or equal to m, correct. So, the corresponding set of vectors is called the signal space representation, also known as constellation of the given signal set. So, correct. Now, from the orthonormality of the basis phi and t, it follows that the energy in each of these given signals can be computed as follows. So, the energy of the mth signal is simply the square of the length of the vector, or equivalently the square of the Euclidean distance from the origin to the point Sm in the n dimensional space. So, thus any signal can be represented geometrically as a point in the signal space spanned by the orthonormal functions phi and t, correct. Now, for such a case, if you have two signals in this space, let us say sk t and sl t, correct. Now, both of these signals can be represented in terms of orthonormal functions as follows. And now, if you try to evaluate this integral, right. So, this is nothing but the correlation between the two signal SKT and SLT, which we can write by definition as just a notation, correct. So, each of this signal can be written in terms of vector, and then it is easy to see that basically this will be equal to and this will indicate by the dot product of the two vectors Sk and Sl, correct. So, what this shows that the inner product of two signals is equal to the inner product of the corresponding vector, okay. It is also important to realize that there are infinite number of possible sets of basis signal for a given signal space. For example, for this case, when we started with S12, S23, S33, S4t this way, we generated this set of orthonormal basis signals. But it is important to note that this orthogonalization procedure does not provide you unique orthonormal basis signals, correct, because it all depends on the way we have arranged S1t, S2t, S33, S43. If I had arranged it little differently, correct, for example, if this was S1t and this was S2t, then I would get a different set of orthonormal basis signals, correct. So, if I get different orthonormal basis signals, the vector representation will also change, but it is important to note that the dimensionality will not change, correct. So, in this case the dimensionality will still remain 3, correct. So, and the representation of these signals as a vectors will obviously change because the basis signals are changing, correct, but the configuration of the vectors will not change, correct. So, the length of the vector will remain the same, correct, the dot product between the two vectors will remain the same as you would get the answer in the earlier basis signal set, correct. So, that is important to note. Fine. So, just for the sake of completion, I can just provide you another basis signal for the example on hand. For example, I could have use these 3 basis signals. So, I will just call them so this is from 0 to 1, this is time, this is 1 to t, and this is from 2 to 3, correct. So, these 3 basis signals also will be able to represent the signal space spanned by these 4 signals. So, this proves my point that the orthonormal basis signal set is not unique. Okay. So, with this we end a module on the signal space representations of signals. Thank you.